Okay, so hi all, welcome to the topic of my presentation is context-aware anomaly detection in automotive CAN without decoding. So my name is Ravi Rajput. I'm a principal architect in information security at Neotech Global. Uh, I have expertise in telecom and automotive cybersecurity, and I had asked of vulnerability research project. I had spent my life in advanced pen testing. I had launched an AutoHack OS, which is an operating system designed for automotive pen testing, and it was launched in Black Hat Arsenal in Asia. And it has reached millions of downloads now, and it has been used by OEMs. I'm a core team member of a telecom village at DEF CON. I had presented at DEF CON, Black Hat, HITV, NullCon, HitCon, and several besides conferences. So the agenda of today's talk is we will talk about how the canvas is blind and how the machine learning can detect the anomaly without the use of decoding it. So we will go ahead with the demo as well. We will talk about the working mechanism of the models that are the algorithms that will be used, and we'll discuss about the key findings and result and the deployment possibilities as well. And later we'll have a Q&A. So Canvas is blind, right? The problem with Canvas is there is no authentication, encryption, or integrity check. There is no sanity checks. It's a broadcast architecture. So every ECU can receive the message or can send the message, right? No built-in support for access control or anomaly detection. The traditional detection is based on the rules that catches the patterns. uh, there is no state awareness. Okay, it's a stateless protocol. Canvas can is a stateless protocol. So it allows a malicious actor to inject the inconsistent state, triggering the alerts. Over here, we will use the machine learning algorithm to detect the CAN anomalies. It rely heavily on the protocol decoding. The traditional way depends on the decoding, while the approach that can be used for anomaly detection in CAN is supervised and unsupervised learning. While the challenge with the supervised learning is that we need and can data set labeled to understand the anomalies, while the unsupervised learning doesn't need that, and that is the reason we will go with unsupervised. And as if we see Canvas as like CAN messages as a sequential and a time sensitive, we will be able to detect the anomalies. So anomalies doesn't mean that one wrong message, it's a break in the context. So, the problem that I was trying to address was different, like every vehicle model have a different structure, signal, meanings and encodings. So it's not scalable across the fleets or vendors. The solution for it is try to find out the frequency of CAN IDs and the burst patterns, payload byte entropy, timing deltas, and sequence correlation. The algorithm that can be used for detecting will be LSTM, and the better version will be LSTM VAE. So it can learn what a normal sequence of CAN messages look like, and when the frequency changes, what will be the correction error. So autoencoders trained on normal behavior, and it reconstruct the expected output. Whatever the deviation is, if it is above some threshold, it is detected as an anomaly. So and then why LSTM and LSTM VE? So LSTM is long short-term memory network. It knows so it knows what is to forget, what is to remember, and what is to be like. So it knows the memory to be remembered. So it sees the whole network as like the whole messages as a what we say the sequence. Okay, rather than picking up the messages separately. It's like a musician trying to play a music, and if he misses a note or do some minor mistake, the whole music is disrupted. That is how the LSTM also works. It's a sequential thing. So the way adds a variational interface inference to the standard AE. It adds actually latent distribution. So the intuition behind this LSTM is feed-forward network. Okay, so it maintains like it has three gates: what to forget, what to remember, and what to output. Okay, so it maintains the cell state. Okay, so why the neural net fail for the sequence is there is no understanding of sequence flow and the time dependencies. So if we map the message IDs with the time, we will be able to understand the pattern. And if there is a burst, there is a change in the pattern, we will be able to detect the anomalies above some threshold. So the sequence to sequence model will be like input sequence encoder. It will be fed to latent vector, then decoder, and it will try to reconstruct the sequence. Okay, the reconstruction error is typically mean sequence error. Okay, it will try to minimize this sequence error, but it still gets above. It will try to detect that. It's something like if I'm driving my car from 0 to 10 to 20, then 25, 30 kilometer per hour, but there is a message saying that 0 then 10 kilometer per hour, but then all of a sudden there is 100 kilometer per hour of message, then it is the change in a pattern. This is what LSTM detects. So uh, so that there is an input that you have to the input will be the sequence of can frames, typically shaped as sequence length, and we have to do the feature extraction engineering, like feature engineering, and then read the encoders will read the input sequence one time step at a time. That anomalies are there. So the LSTM way is basically the extension of autoencoders with a latent variable on the distribution. Okay, so basically it has loss function is into two parts: reconstruction loss, which actually measures how well the sequence is rebuilt, and the KL divergence loss, which measures how far latent distribution deviates from the standard normal. So it's a uh, while you can consider this autoencoder as a not a distributed, but this can be thought as a distributed as like the way uh, the major part of way is latent sampling. Okay, which introduce the controlled noise. Okay, that's a major difference between VE and LSTM autoencoder. Why uncertainty matters in a CAN or anomaly detection is automotive networks are noisy and busty. Static threshold can cause false positives. Okay, need models that can express confidence, not just anomalies. And how this LSTM way tackles uncertainty is learns the distribution of a valid behavior rather than a fixed pattern. It produces a latent vector with a mean and variance and samples from that mean and variance to the variability and more tolerance to the natural deviation. So if we take about like if we talk about the real life example, replay attack basically detected with the wrong timing, that is a latent shift draft KL spike in the divergence spike, while the fuzzing is detected on the entropy spike. Okay, so the data pipeline for the demo that we will do currently is we will collect the log for the normal canvas for training the data for training the model, while the attack.log will be used for evaluation, and it will extract the timestamp, can id and payload byte. Then it will filter the this non-standard form frames and discard that. Will try to find the difference, the difference in timestamp as a delta t, then the entropy and the frequency of can id in a sliding window. Feature engineering constructs a sequence of windows basically and tries to normalize the min max or z score. Then we will train the model and then inference scoring. So rather than going through the slides, let's do some demo. The simple demo will be by using the canvas. By using ICSame. Okay, so I'm trying to increase the speed and left and right. Okay, so what we will do here is we'll try to capture the normal log. And we will do some normal activity. Okay, and uh, we will first this other can IDs as well. So the main target can ID will be on the door, that is 19B. Okay, so the door lock and unlock mechanism, that is 19B basically can ID. So we are capturing that. Okay, so now it must be enough. Yeah, perfect. Now on the one screen, we will try to fuzz on particular can ID 19B, while on the second we'll run the we'll capture the log. Okay, as you can see here, the door we are basically fuzzing on the door can ID. We'll give 5 more seconds.
Hey, Ravi, just a heads up, you got 5 minutes left for your presentation.
Okay, just 5 minutes.
Yeah, they need 5 minutes to get the next speaker on before, so sorry.
Okay, so rather than going on this, I will show you the already experimented one and the results. So we'll get the logs from here and on this, and once you run, you will find the feature engineering, and you will find the time delta and the entropy. Okay. The sequence generator will uh, get the MSE loss, and you will get the MSE loss graph. Then the model will try to detect the anomalies over the top 5 CAN IDs. Okay, over here you can see the CAN 19B is detected. There is little bit of a false positive. While if you can see on this VE, which is more robust algorithm, you will see that 19B is detected as highest entropy anomaly detection. And you can see the peak of this CAN IDs. While you can see this, the entropy is very much over here, which can be concluded that anomaly. And these are the other graphs that we can discuss, but due to the lack of time, we'll go with just a simple output of this. I will publish this on GitHub as well after the talk. And it will give you the reconstruction error that we had already talked about. The reconstruction error will be high. That is how the anomaly detection will be detected. So let's talk about the key findings. The unusual or previously unseen IDs. Sorry. The unseen IDs during replays in rare IDs showing up high frequency will be detected as CAN anomalies. Payload entropy spikes and timing deviations will be shown as anomalies. While you can go ahead with Way is another version of like LSTM's Way is another version for the replay attack detection. And for the deployment possibilities are you can deploy this lighter version of this model on your ECUs as well. And this can be the best option for your VSOC as well as SIM solutions. Yeah, so let's move to the Q&A.
Maybe we have time for one question. I think we might have time for one question. We only have 2 minutes left. Is anyone in the audience got anything to ask? The question was, what is the application for this? Is this specially designed for intrusion detection?
Yeah, currently it is. I'm currently experimenting on intrusion detection only. Still not have figured out for the prevention part.
That good? Okay. I think we're out of time now. So thank you so much, Ravi, for your presentation. And yeah.
Thank you. Thank you so much. Dhanyavad, Abar. You can reach out to me on social media anytime, InfoSec Ravi or Frustrated Researcher. Thank you. Thank you, Ramit. Thank you.